Good morning, everyone, and thanks for attending ANSHM annual workshop. The topic of my discussion is debonding detection in rebar reinforced concrete structures using second harmonic generation of longitudinal gyro waves. As seen in the literature, the debonding present between the steel rebar and the concrete can cause reduction in the strength. It can reduce the slip resistance between the steel rebar and the concrete and can ultimately reduce the bending capacity of the beam, causing the failure of the structure at earlier stages. So traditionally, most researchers have used bulk waves for damage detection in the structures. However, in the last few decades, guided waves have been a very hot topic for damage detection in various types of structures. So they can cover longer distances and there is no need to inspect at every particular areas for damage detection. As discussion is about damage detection in cylindrical structures as rebar, so it is worth to mention that there are three basic gyro wave modes in cylindrical structures, which are longitudinal, flexural, and torsional, and they depend upon the wave motion of the guided waves in the cylindrical structures. For for bare rebar, there is only one guided wave mode as seen by many researchers up to 300 to 350 kilohertz. And as you can see that if a cylindrical structure is embedded in concrete or any other material, the number of guided wave modes increases. Talking about the literature for damage detection in reinforced concrete structures, many researchers have used linear features of guided waves for damage detection, such as change in the amplitude, time of arrival, velocity for damage detection in reinforced concrete structures. The data is collected at healthy state and the damaged state, and then it is compared to uh, to detect the damage in reinforced concrete structures. So researchers have used debonding damage detection and corrosion damage detection using the linear features of the guided waves. However, nonlinear features of guided waves can be used for damage detections. Nonlinear features can be described as higher harmonics or combinational harmonics for damage detection, which are generated from the presence of damage or other material nonlinearities. So recently, in reinforced concrete structures, Mawsony and NG has used deep bonding damage detection using nonlinear features of guided waves. And similarly, surface cracks and other cracks in the reinforced concrete structures have been detected using nonlinear features of guided waves by many researchers. However, the debonding type damage between the steel rebar and the concrete uh, has not been thoroughly studied by the researchers in the past. So the topic of this presentation will be to detect damage in reinforced concrete between steel rebar and the concrete. So first to um, highlight how the second harmonics are generated due to the contact type damage in structures. So when the wave interacts with nonlinearity or damage, uh, it, it it interacts with the cracks. It has two components, a tensile and a compressional. Only the tensile component is reflected back, and compressional component passes, causing the opening and closing of the crack. So this phenomena is known as contact acoustic nonlinearity and was a helpful feature of the nonlinear feature of guided waves. So for damage detection in reinforced concrete structures, numerical and experimental study will be discussed to detect damage using this methodology. So as an overview, when the wave is excited from at the bare end of the rebar and when it travels into the embedded rebar, various guided wave modes are generated, and when it travels to the debonded region, it interacts with the debonding, and due to the contact effect, second harmonics are generated, and these second harmonics are generated will travel into the embedded rebar, and it can be received at the other end of the rebar, and it can give us a indication of the presence of damage. So it is it is worth to note that gyro wave modes present in the bare rebar and embedded rebar. For the study, a 20 millimeter diameter rebar is selected, and gyro wave modes are found using disperse software in bare rebar, which is shown by the blue line. And as you can see that there are a lot of gyro wave longitudinal wave modes present in embedded rebar in the concrete. So in order to compare, check that how many uh, wave modes propagate into the bare rebar and the embedded rebar. First, a rebar is modeled in Abacus. A 20 millimeter diameter rebar is modeled, and 80 kilohertz 8 cycles hanging window signal is excited at the one end of the rebar and is received at the other end. So initially, the rebar is modeled as a plane and with the ribs to compare if the ribs poses any changes in the time domain or in the signal of the bare rebar. It shows that it doesn't affect the propagation of the gyro wave modes, and hence therefore plane rebar can be used for study of the debonding type damage in the reinforced concrete structures. At the below it shows the schematics of the sample which is used for experimental and numerical study. So the cross section of the sample is 100 by 100 millimeter with a 20 diameter rebar embedded into the concrete. The guided 80 kilohertz signal is excited at one end of the rebar, and the signal is received at the other end. The time domain signal received for for the bonded and the debonded sample is shown here. As you can see that the presence of time domain signal does not give much indication of the presence of damage, and therefore nonlinear features can be helpful in this regard for damage detection. So an image of the simulation. It's showing us the opening and closing um, of the debonding region, and this is due to the contact effect. And these surfaces between the steel, rebar, and concrete are called breathing surfaces, as they can open and close when the wave propagates through this region. And similarly, the beam, which is analyzed using the numerical study, is um, is tested using experimental setup, which is shown here in this picture. And so the beam is the signal excited using NI system, and it is amplified using a cone height amplifier, um, and then it is excited at the one end of the rebar, similar to the FE. And then when the wave interacts with the deep bonding, and is then received at the other end of the rebar, and the signal is processed through NI system and is analyzed using the computer system data. So how the wave is excited, the 10 millimeter diameter PZT is installed at either ends of the rebar, and initially uh, to compare the signals of the FE and experiment for the bare rebar, 80 kilohertz signal is used, and it shows the significant match between the FE and experiment for bare rebar 80 kilohertz, and then it is compared with theoretical data, which is through disperse software, and it is compared at different frequencies. Therefore, this PCT setup can be used for excitation and receiving of longitudinal guided wave signal. Next, the reinforced concrete beam sample is tested for the 80 kilohertz signal, and this is the data, which time domain data, which is compared for experiment FE for bonded and debonded sample, and it was a very good match between the time domain signal. However, again, the time domain signal does not give much information about the presence of damage, as you can see, between the bonded sample data and the debonded sample data. And then for detecting damage using nonlinear feature, fast Fourier transform was applied onto the time domain signal, and as you can see, there is a clear indication of the presence of second harmonics, which is represented by the amplitude A2 at 160 kHz, as the excitation signal is at 80 kHz. So second harmonics are observed in both numerical and experimental. And below, the time frequency spectrum is plotted for FE and experiment for each bonded and debonded sample. If we look at a bonded sample, there is no presence of high harmonics, which is 160 kHz. However, for debonded sample, uh, high harmonics, there are second harmonics are present at 160 kHz, and which represents a clear indication of the damage. Next, different size of the debonding and different indication of the debondings are numerically studied, and these are defined as cases N2 to N5. And on the right, you can see the time domain signal of this data, and fast Fourier transform are plotted here, which clearly represents the presence of second harmonics in each case of debonding. So the next challenge can be to detect the location of the debonding, which is possible through this equation, which is formulated by the theory the difference in the time of arrival of first harmonics and the time of arrival of second harmonics, which is represents delta t. So the dl is the location of debonding from either end, can be detected using this equation. So Vg S represents the group velocity of first harmonic steel, and the S2W omega represents the group velocity of second harmonics, and similarly subscript C represents for the concrete. So as we know that there are multiple guided wave longitudinal wave modes present in the embedded rebar. So in order to select the group velocity of the longitudinal wave mode, it is important to find out which wave mode is the most dominant wave mode. So for this, wave number frequency spectrum analysis is carried out to find out which wave mode is the most dominant wave mode propagating in the embedded rebar. So wave number frequency spectrum is carried out for embedded region and also the bare rebar. So it is found out by wave number frequency that L04 wave mode is dominant at 80 kHz and also at the second harmonics at 160 kHz. The group velocity of L04 wave mode will be used for location estimation. And for bare rebar, the L01 wave mode is the dominant wave mode which exists. As discussed in the last equation, the time delay is also considered, and location estimation. As the wave interacts with debonding, there can be delay in the generation of second harmonics. So this delay is calculated theoretically. Theoretically, the second harmonics should be present uh, at the location of 2.3 into 10⁻⁴ second. However, by carrying out the time frequency spectrum analysis at the location of the debonding, the delay is found out, and this delay is incorporated in the location estimation of debonding. And this data shows the time frequency plots for all the debonded cases, and they all clearly shows the presence of second harmonics due to the debonding. So, and this shows the time of the arrival of L04 wave mode at excitation frequency and also at the second harmonics. So also for is time frequency plots are shown here to indicate the data um, about the time of arrival of second harmonics and excitation frequencies. So the information about the time of arrival of first harmonics and second harmonics are achieved through time frequency plots, and this information is used to detect the deep bonding type damage. As you can see that these are all cases where location is estimated, uh, and it lies very well within the debonding region for each of the debonded case. So experimentally tested sample also gave a good indication of estimation using this methodology, and it is around 356 millimeter as compared with the numerical of 351 within the debonded region of 300 to 400 millimeter. So in order to conclude, we can say that contact acoustic nonlinearity is a phenomenon can be used to detect debonding between the steel rebar and concrete. So nonlinear features are helpful in damage detection in reinforced concrete structures, and they do not require potential baseline data for healthy states. And so numerical and experimental study is highlighted in this presentation. And for debonding location estimation, time frequency plots, and wave number frequency analysis is carried out for location of debonding in the reinforced concrete structures. In order to quantify the damage, we can also plot non-linear parameter, which is which can describe as a ratio of amplitude of the second harmonics to the amplitude of the excitation frequencies, and it is plotted at different lengths of debonding, which were the cases from N1 to N5, and it can see that non-linear parameter increase as the debonding length is increased, and this non-linear features has a potential for baseline field measurements and helpful in damage detection. Thank you.